Hey everyone, it's Sofox again with the Arduino projects book, and today we're doing 06 Light Theremin. Now, basically, for this thing we'll need this. It is called a piezo, a small element that vibrates when it receives electricity. When it moves, it displaces air around it, creating sound waves. Now, by hooking it up to the Arduino, we can make it make sounds. And the question is, how exactly does it do this? Well, it's pretty simple. You basically do, like with a lot of electronics, you go high voltage and low voltage and jump back and forth, creating a frequency. Now, if you do this by using an analog write signal, you might change the amount of time it's saying at a high voltage, but as you can see, the frequency is pretty much exactly the same, the period, so to speak. But by using the function tone that comes with Arduino, you can actually set it to go back and forth at a very low frequency or at a very high frequency. So that's what it's hooked up to. Now, in case you're not sure what the Theremin is, it was used in the classic black and white era of Hollywood to create very off-putting ooh sort of sounds. It basically is great for classical analog sound effects. It's got a very distinctive thing, and the key thing about a theremin is you actually reach towards it and control it by pushing your hand closer and further back from it. It actually senses you. It's pretty cool like that. A lot of electronics. We're not going to be doing exactly the same thing, but we're going to do something along those lines, just sort of. Instead of using just electronic signals, we'll be using photoresistors. But before I get to that, I am going to skip ahead and I'm going to skip ahead and try to do something that they didn't actually ask me to do in the instructions. So, as you can see, here is our servo and everything from our last experiment. For now, we shall be removing the capacitor and removing the servo itself. Goodbye, servo. We had good times together. Next, we're going to actually hook this up just as it says. So, we plug this here, because that's what it does. Oh, damn it, it takes up a lot of space. I got to make sure I plug this in and it's still able to... Okay, they don't make it seem this is going to be this difficult. I mean, I've got it the very furthest wrong, and I'm not even sure if the pins are available. Okay, let's make it here. So, 30 is one pin, and 26 is the other. So yeah, we've just about got those lines exposed. So according to this, we need one going to negative, and the other going to 8. So let's see if I can actually get the right ones this time. So, okay, one going to 30, and this is 26. Yes. Oh, damn it! Come on, you can do it. 26. So this is 26. I said this is 26. Here we are. And the other, and this is 8. Now let's look at the side and make sure I plug it into 8 this time. Good. Good. So far so good. And now we'll connect it the other end to ground, and we'll do it using this. Okay, that looks good. Now you notice I've kind of left my potentiometer in, and I haven't yet connected the light theremin. There is a reason for that, and you'll see presently. Okay, so here we've got the experiment from last time, our mood cue. Let's just make a new one, and let's save it. Oops, wrong one. Save it, and it's L-I-G-H-T, T-H-E or E-M-I-N. Save. Okay, and so now I've deleted the thing. So first of all, I'm just going to quickly copy the potential pin and potential value from here and save. And then what I'm going to do, serial copy this function over as well, because sometimes you need to put that there. And then what's this? Oh yeah, of course you can read the potential value by doing this and then map it to this. So I'm pasting this code right here. So oh, wait, hang on a second. Oh. Yeah, tone apparently is occupied, so I'm putting down note. Okay, so let's take a quick look at what we got so far. The potential, because we've got our potentiometer hooked up from last time, which for the record is just, basically it's got one voltage, one in ground, and one in an analog reading pin. And we've still got our potential value. What happens is we read the value from the potential pin, print it out. So just as a quick thing, oh right, first of all let's plug in our Arduino. Good. Now, okay, and so then we go to Tools and Serial Monitor. And okay, so it's still reading our potential value. once it's plugged in properly, that is. There we are. So I'm going to skip ahead. Instead of waiting for the light theremin, I'm going to follow the instructions of the book just to get this tone thing putting something out right now. So the idea is that you put out a pitch. Yes, it's not an int, it's a pitch. It's not a note, it's a pitch. So the pitch takes the potential value, which is between 0 and 1023, and maps it between 50 and 4000. 50 and 4000. So that means if the potential value is 0, then it'll come across as 50, and if it's at its maximum value, 1023, then it'll come across as 4000. That way we get perfect mapping and it doesn't get really, really weird. So then we have to do the tone, which is tone, which is 8, because that's, technically this is bad practice. They should have said, you know, like int, const, and something like, I don't know, piezo pin, and then set that to 8. Technically, it's kind of bad practice to have the pin only listed right down here, because, you know, if you have to rewrite the code, it might be hard to understand, and if you change the pin, then you might have to look for all the instances of 8, and then you can't bind the 8. So this is why what I'm doing is actually smarter than the book, which I have known to be. And of course, yes, and we'll switch this note to pitch. So we define pitch there, we get the pitch there, and type the pitch here. And then we set 20, and I'm not actually sure what 20 stands for right now, but oh yeah, and how long to play the note. Try 20 milliseconds to start. Then call a delay for 10 milliseconds to give the sound some time to play. Okay, so delay. Okay, I am skipping so many steps and just, you know, basically Frankensteining this with the previous experiment, but I don't care. Let's upload the code and see what happens. Okay, we're back here with the actual board. Let's actually click the upload button so that we can actually get the code that we've just written and upload it to the thing. So if I'm right, it should give it tone. Oh, there we go. You hear that? You hear that magical musical sound, which sounds like an angry bee who's had a bad day? That, my friend, is a clear demonstration that this is working. So let's twist this thing and see what we do. Okay. Oh, that's actually really cool. You know, here comes the ambulance or the police officer. It also sounds a lot like some classic video game stuff. I suppose that's because this is technically a square wave, which is one of the most simple sounds you can possibly make, and hence was used in a lot of early video games. And that is my masterpiece. Thank you very much. I am going to stop doing tutorials about Arduino devices and start my great big musical career with this device as my only instrument. Thank you very much. We grabbed the photoresisted thingamabob. Yes. Yes. Yeah, the photoresistor. And the photoresistor is right here. As you can see, I slightly mangled it from the last time we used it, but no worries, no worries. So the idea is that you hit it between one end is the voltage and the other end is the ground, but there is a... Okay, yes. So where's the voltage? That's the voltage over there. Okay, I gotta take out these little things here just so that they don't interfere with everything. Next up, some small cables that go from from voltage to, yeah. So plus is on this side. There we are. So this now is live, line 26. So we take this, we stick this photoresistor right about here, right about here. Come on, photoresistor, you can do this. Yeah, show some resistance. There we are. So we stick one there, and one there. So I need to make sure that this is kind of free because I don't want it to muddle around. So now we take our 10 kilo ohm resistor and stick it from there, from the other end, so 28, and stick the other end in ground. So that means that no matter how, even if this was like a no resistance, it was still this one stopping it from causing it. Remember, never have a short circuit, never so that like you have it from voltage directly to ground without something to slow it down. This resistor will slow that down. But there's still one element to go, and that is having it read by OD or A0. Well, we'll stick it into A1. I mean, I'm sure they won't mind. I'll just code it so that it happens. There we are. So what's happening now is that it's picking it up from, is that this value will be reading the resistance, the voltage. And obviously the more resistance this have, the more voltage will be used over here, and you know, the more the voltage will drop. Basically the voltage will go up and down depending on whether I cover this or not. So let's go over to the coding side and enter in the right coding to make sure this works. Okay, so int sensor, S-E-N-S-O-R value, sensor value, which we leave undefined, int sensor low equals 1023, int sensor high equals 0. Now, sensor value is what we read from the photoresistor. Now, if you're wondering why the sensor low is really high and why the sensor high is really, really low, we'll be explaining that in a second. So, we set the const int LED pin equals 13. Now, we don't need to actually set up the LED because pin number 13 has its own light built into the actual Arduino board itself. We set the digital pin mode LED pin to output, and then pin, and then we digital right LED pin to high. So this will set right in the setup. We'll be setting this to a high pin. Now, the reason we're doing this is because if you remember from our previous experiment, whenever we use the photoresistor, it wouldn't give us a straight value from like 0 to 1024. It would kind of give us something like, sometimes it would be 500, sometimes it wouldn't be 500. It would be like 600. It had a few hundred range, but the exact range was a little tricky to tell. So this whole calibration is to make sure that we actually set what the values actually are. So for instance, if I was to just quickly skip ahead and type sensor value equals analog read, and then A, and the book says A0, but we've been messing around, so it's A1. And if we commented out all this code, because it's kind of my attempt to do with my own messy thing with this, and then if we, well, like, I'll leave in the delay because that's always good to have. And then if we print ln sensor value. Now, I'm going to reconnect this thing. Okay, that's the pin, but I'm just uploading this, and so I know so as you can see, right at the moment it's 800. I put my thumb over it, it's 500. Release it, it's 800. So we have to kind of map the 500 to 800 range directly to the tone. Now I know what you're saying. Well, why don't I just... Well, previously what I did was pretty straightforward. I took this in. I took a sensor value, and originally, and all we have to do is type in what, 500 to about 800, save and run. Actually, this kind of works already. Hang on a second. I'm switching over. Okay, cool. By completely cutting through several instructions in this, I've actually got it working ahead of time. Now, this might not work perfectly, but if you ever do professional work, you'll know that you'll have to make short like this a lot. This is pretty cool. Hang on, let's play around. I think I had more fine-grained control with this thing, but it could also be because the numbers I entered in weren't very selective, but it works. Here we are. So, I guess I've had two working versions of this again, but maybe I should right now do what the book suggests and actually add some basic calibration into it. Let me explain how this works. Okay, so the idea is that we previously hand-coded the 500 and 800 values as the limit, but that's not really the best way to do this. Or at least that's not the way the book says, and for now I'm actually pretending that I'm taking the book's advice seriously, even though it's really only been wrong a tiny amount of times, and even though my ego is incredibly large, I'll be doing it the book's way. So first of all, what we need to do is actually have it so that when you start it up, it spends 5 seconds measuring all the values. Then after it's finished, those 5 seconds are up, it takes the highest value it measured and the lowest value it measured, and then use those as the bounds. So you're actually, calibrating it in a real world environment. That way, if you start it up, if you take this and you bring it to an incredibly bright environment, then, it might end up being 800 is the lowest value. Well, if you take it to a really bright environment, then it might have a different range, so it'll need to adapt. Or if you take it to a dark environment, maybe 500 is a low value. So it's basically about trying to manage stuff like that. Or if you switch out the photoresistor, and then you want to have to keep changing the code every time you change a hardware or its environment. So, first up, we'll be setting 5 seconds. So what we do is MILLIS. This is the amount of milliseconds that's passed since the Arduino started. And we'll say while it's less than 5,000. 5,000, of course, roughly equivalent to 5 seconds. The amount of milliseconds, because Arduinos tend to be hard rebooted every time you run them. You cut the power, and every time you start the power, this is run. The amount of milliseconds is run is from the moment it received power and started up. And another analog read, and okay, that's it. For best practices, I'm going to say int const photo pin equals A1. Now if you remember, the book says it's meant to be at A0, but I set A1 to this. So I'm sweating this to this so that it's easier to run. I just think the code is better that way. If sensor value is greater than sensor high, then sensor high equals sensor value. This bit of code is actually in this form is actually incredibly common. What it basically does is we start at our sensor high at like a really low value, and every time a value is detected that's higher than that, it sets it to that. So that way, if it starts out at 0 and you give it 10, then it goes up to 10. Then if you give it a 5, then it stays at 10. Then if you give it a 20, it goes up to 20. Then if you go a 0, then it stays at 20. So basically, it always goes up, it doesn't go down, and by the end of it, you're sure you've got the highest value. There's a lot of cases in general programming where you want to get the highest or lowest value, and that's pretty much one way of doing it. Set something to 0, and every time a potential value is higher than that, you set it to that. Now, if sensor value is less than sensor low, then sensor low equals sensor value. So this pretty much is the above one. It just works in the opposite direction. Every time you set the sensor low to a high value, and every time it gets a lower value than that, you set it to it. So we've set the sensor low and set the sensor high, and then after that's done, we digital write, and the LED pin is set to low. So I don't really need to explain this bit. Basically, the light goes on and lets you know it's calibrating, and then after the 5 seconds are up and it's finished calibrating, after it leaves this loop, it sets it to low and lets you know you're ready to make music. Of course, the other sign is probably that it starts making music. So, The next thing is to make sure that the sensor low and sensor high is set to these things. So sensor low, sensor high, and I think that's pretty much it. Let's upload that and give it a go. Okay, so first of all we plug this back in, and next, okay, that was from the last thing, we upload our new code. Okay, so they should be, okay, there it is. Okay, so that's it. Now I'm closing it and I'm taking it off. I think this light is that, yep, I think we did it. I think over here is the 13 light, so there we go. Okay, so as can be seen before, you have the, let's see what happens if we just refuse to calibrate it because we are bad people. So you can see the light goes on telling us that it's being calibrated, but we're not actually, covering it, so it's just getting, yeah. Basically, because its lowest value and highest value is so close to each other that even a tiny change can suddenly have radically different results. That's why calibrating is important. You need to know the limits of how it's going in one direction and in the other direction, otherwise it all gets screwy. So let's try one more time, and this time let's do a proper calibration. Light goes on. Okay, so that's light, and then we close it to give it its lowest value, take it away, close. That's pretty cool. It's like my hand is a barcode or something. Okay, I think that's considered a success.